Okay, today we're going to be looking at series and parallel circuits. So, as you've probably already come across, we can divide circuits into three basic categories. So, series is when our components are lined up kind of in a row. Now, you can take all the components within a circuit and basically divide them down into resistors. Because every component has a resistance, you can essentially find the combined resistance and then make it into a circuit just represented by resistors, to really simplify things down. So this is a series circuit, and this is a parallel circuit, where the components are obviously parallel to one another. Oops, done it again. There we go. And then we have another one here. It's meant to be joined there nicely. And here's our parallel circuit. And we also have a mixed circuit, which is just a combination of the two, the series and the parallel. We can have different branches coming off our circuits to make them a wee bit more complicated. There we go. When we're considering our different, so this is a mixed, sorry. So when we're considering how the voltage and the current act in these types of circuit, we'd have to look at them all separately. So we're going to look at the series circuit first. And we're going to consider, we'll just redraw a nice little series circuit here. And it's got some voltage which we'll call our total voltage. And if we were to take a voltmeter, we would be able to read the voltage over each of these resistors. So that would be V1, this would be V2, this is R1, R2, and so we've got our supply voltage is equal to our voltage, our first voltage plus our second voltage, and in a series circuit the total voltage is spread out over all the components. So from our equation V equals IR, we can deduce that the total resistance, now current is the same wherever we are in a series circuit, it doesn't change. So V equals IR is going to be the total, I times the total resistance times the current times the resistance in R1 plus the current in R2, and so on and so forth. And that then gives us, for a series circuit, the total resistance is the resistance over is the sum of all the resistances in series. Now this is because of the way the current flows. Resistance is something that opposes the flow of current. So to get the current to flow through it, we will have, there has to be a greater potential difference to push those electrons through that resistor. So you get the bigger potential difference over the larger resistance, and therefore the voltage is added up, and that's how we get this, come to this very simple equation. So let's do a worked example. We've got an ammeter here. And this is 6 volts, this is 4 ohms, 5 ohms, 3 ohms. So we want to calculate the total resistance and the reading on the ammeter. Okay, so first we're going to calculate the total resistance. So the total resistance is going to be R1 plus R2 plus R3, which is 4 plus 5 plus 3, which gives us 12 ohms. Nice and simple. Now, you could, if you wanted, just draw another circuit, and instead of having 3 resistors, you can turn that into one 12 ohm resistor, and then you've got a nice simple circuit diagram to then work out the current, because we've got V equals IR, the voltage is 6, we don't know the current, and that's times 12 ohms. So the current must be 6 divided by 12, which is 0.5 amps. You don't need to do this step if you don't want to. Sometimes if you're dealing with a more complicated circuit, as you work out in the mixed circuit problems, as you work out each part, simplifying the circuit down by combining resistors into one resistor can sometimes make the problem a little bit easier. Obviously for this one it's just being a bit pedantic, but it gives you the idea of what's happening. So let's consider the features of a series circuit, and these are important to remember. So 1, the current is the same at all points. 2, the resistances can be added together to work out the total resistance. 3, the potential difference, i.e. the voltage across each resistor, depends on the resistance. 4, the total potential difference is equal to the potential differences across each individual resistor. So that's our series circuits. Next we've got our parallel circuit. So let us draw a simple parallel circuit, and this time we're going to draw it with some ammeters in place. So here's our ammeters, and now we've got our resistors. We'll do 3 resistors, and we'll do a voltmeter here. And that's over this device. And then we are closing our circuit up. It's closed very badly, it's a wiggly one. So, say we have, here's our cable, and we've got our electrons flowing down here nicely like that, and they have to go in this. This is the way they have to go, because there's just, they can't escape this cable. It's like a river flowing. What if we split our cable in two? We've got, or if you can think of a flow of electrons a bit like a flow of water down a river, and now we've got a split in the river, and obviously that some can go down this way and some can go down that way. Now if we continue with our analogy of a river, say we had a really narrow bit and a really wide bit. Here's, although it's water, we're thinking electricity. So here's our down here, where it's wider, you can get more current flowing. This one's narrower, and we'll get less current. So this is like, if say we had a large resistance, a large resistance is going to is going to slow the flow. It's going to make it harder for the electricity to flow that way. This is going to be a smaller resistance. The current's going to be less inhibited coming down here, and that's what we see in a parallel circuit. The current comes here and it can flow down the different branches, and the amount of current in each branch of our circuit depends on the resistance in each branch of the current. However, the voltage over the series current is the same as our voltage here. So we know, so the total current is going to be the same as the current in each branch added together. Now we can apply Ohm's law, so current is V over RT, is V1 over R1 plus V2 over R2 plus V3 over R3. However, the voltage in each branch is the same, so if we divide through this equation by V, we'll just get 1 over RT is equal, the total resistance is 1 over R1 plus 1 over R2 plus 1 over R3. So the total resistance of the whole circuit is given by this equation, and this is for our parallel circuit. So let us do a little problem involving parallel circuits, just to see this in action. So we have this following circuit, we'll just draw it. Here's our ammeter, and it branches off like this. And we've got a total voltage of 6 volts, and this resistance is 5 kilo ohms, and this resistance is called R2. So the total resistance is RT equal to 3.3 kilo ohms. Find R2 and the current in this resistor. So the first step is to find out the resistance. So we've got 1 over RT plus 1 over equals, 1 over R1 plus 1 over R2. So our total resistance is 3.3 kilo ohms. So that's going to be times 10 to the 3, and that's 1 over 5 times 10 to the 3 plus 1 over R2. Rearranging all that, we get R2 is going to be 10,000 ohms or 10 kilo ohms. Now we need to calculate the resistance in this circuit. Now we know the voltage is going to be 6, so V equals IR, voltage is 6, current is what we want, and the resistance is 10,000 ohms. So the current will be 0.0006 amps or 0.6 milliamps. So the features of a parallel circuit are the total resistance is given by this formula. Secondly, the current in each branch of the parallel circuit adds up to the total current in the circuit. Thirdly, the current in each branch depends on the resistance. The lower the resistance, the higher the current. Just think of the principle that the current is going to take the route of less resistance. For the potential difference across each branch of the parallel circuit is the same. Okay, now we can take what we've learnt with the series and parallel to apply it to mixed circuits. So, at first these can appear complicated. Let's do an example. We'll change our power supply this time, and we've got 100 ohm resistor, and then we've got splitting into a series part of a 500 ohm resistor, and then we have 200 ohms, 300 ohms. Now we can just close it all up like this. So what we want to do is we want to step by step reduce this mixed circuit into something which has one resistor. So the first thing is to look at the part that is in parallel. So here we've got a 500 ohm resistor, but here we have two resistors in series. So in the parallel part, we're now going to go further, hone in on this part here, which is in series. So for this part here, the total resistance in this arm of our circuit is going to be using this formula for series, because these two resistors are in series, so it's 200 plus 300 is going to be 500 ohm. Now we could, let's just redraw this. There's going to be lots of redrawing, I'm afraid. There's our 100 ohm. Here's our 500 ohm. And now we've got another resistor here. Oh, it's terribly drawn. We can close it. So this arm has got a resistance of 500 ohms. So the next step is to deal with the whole parallel part of the circuit. So for here, our total resistance for the part that's in parallel will be R1 plus 1 over R2, which is 1 over 500 plus 1 over 500, which, working it all out, will get a resistance of 250 ohms. Now we can draw it again. 100 ohm. Now we no longer need to draw our part that's in parallel, because we found the total resistance of that part of the circuit to be 250 ohms. So we can now find the total resistance in our circuit is just what we use for our series. 100 plus 250 gives us 350 ohms. And so by stepping down and using these, what we know about series and parallel circuits, we can step down and turn a mixed circuit into something that is altogether more manageable by applying Ohm's law at each step and just taking our time and being careful. So I hope that helps.